Hi, my name is Massimo Banzi and I'm one of the co-founders of Arduino. Welcome to this series of video about the Arduino starter kit. In this particular video, we're going to start learning the basics of all the components we're going to use in the rest of the videos. So what we see here is a set of electronic components, and today we're going to build a very basic circuit. We're going to use a small LED connected to a button, and when you press the button, the LED comes on. It's a very simple electronic circuit that doesn't involve our Arduino board at all, and it's designed for you to understand all the basic elements that make an electronic circuit. So what is an LED? The LED is a small source of light. You can imagine it's like a light bulb, but it's more efficient because it doesn't generate that much heat because it's an electronic component based on a semiconductor. So LEDs are very convenient for us because they work at a small voltage. So they can be powered by a small battery or the voltage that you can get from an Arduino board. So what is a circuit? A circuit is a series of electronic components like this LED or this button connected together using wires. Electricity can flow through the components, and each component is either able to transform the electricity into something else, like light, like the LED does, or, for example, the switch is a component that can open and close a circuit when you press on it. This particular button that I have in my hand, it keeps the circuit closed until I press the button, and then it closes the circuit. Closing the circuit is like a little bit like when you open a tap. You let the electricity flow through the button. Electricity, you can imagine, is like water, and the wires that we are using to make the connections are like pipes. So the source of electricity is essentially the equivalent of something that pushes water into the pipes. So the first circuit that we're going to build is going to have a source of electricity pushing the current through the wires, a number of wires that connect to the button. Then the button will open and close the circuit, and when the circuit is closed, the current will flow through the LED. And then we will use another component that I have here called resistor. What happens is that the voltage of our battery is too high for the LED that we are using. Just to give you an idea, we're going to be using a source of electricity operating at 5 volts, which is the standard voltage at which the Arduino board operates. But this LED is only going to need about 1.7 volts. So how do we make sure that the LED doesn't take too much current? Well, we're going to use a resistor, and this resistor is going to limit the amount of current that flows through the LED, keeping it at the optimum amount of voltage and current. How do we make the connection? Well, actually, what happens with circuits is that you can take wires and you can wrap them around and you can create circuits like that, but it's not very practical. If you want to do a lot of experimentation, if you want to move components around, if you want to try different kinds of circuits, wrapping wires around is not exactly the best idea. So what we're going to do, we're going to use this component that you see here. It's called a breadboard. The breadboard essentially provides a set of pre-arranged connections, and each one of these holes is actually connected underneath with a metallic spring. So when I plug a wire into the breadboard, the spring will hold on to the wire and it will connect to all the other holes in the same line of holes. So let's have a look. For example, this line of holes that I am pointing to at the moment, they are all connected together. So if I plug this wire in this hole, all the holes in the same column are going to be connected to this wire. So if I take, for example, this resistor, and I plug the resistor in one hole in the same line, for example here, this is okay. So at the moment, the resistor and the wire are connected together. If I move this wire to the hole next to it, they are not connected anymore because only the wires in the same column are connected together. So to explain this concept a bit better, I have prepared here a circuit that contains a lot of all the basic elements that I told you about. This is the resistor, this is the push button, this is the LED, and this is a wire. So what's missing here is the source of power. What a circuit needs in order to operate is a source of electricity. In this case, we're going to use the Arduino board as a source of electricity. The Arduino board can be powered through a battery or through a USB connection, as you can see in this particular situation. We're not going to use the intelligence provided by the Arduino board. We're just going to use the power that you can take from the Arduino board in order to learn how to build the circuit on the breadboard. So we're going to connect this wire to the other leg of the resistor. You will notice that actually the holes on this side of the breadboard, they have a different pattern. So why is this? Because actually these two lines of holes, they follow a different connection pattern. So the ones that cover the main area of the breadboard, as I said, are all connected along the column, while these lines are going all the way from one end to the other. So these are two separate strips of holes, and each one of them is connected together. So for example, if I plug this red wire at the beginning of this line of holes, I'm actually connecting 5 volts to every single hole that you can see on this line here. So this means that the resistor is now connected to this hole. Now I'm going to take this black wire and I'm going to plug it in one of these two holes that are marked G and D. G and D is the ground. It also represents the minus on your battery. If you look at the battery, normally there's a plus and a minus. So 5V represents the plus on this ideal battery, and the minus is here represented by G and D. So if I connect the black wire to the other line on the breadboard, now I have connected 5 volts, the first lines of holes, and the black wire to the second line of holes. Now, if everything is done correctly, if I press the button, I'm going to connect the resistor to the LED. This will complete the circuit and the LED will light up. Wow, okay, it's working. Okay, that was good. So the ability to convert electricity into another physical phenomena that we can actually experience in the real world makes the LED a transducer. So the transducer is a component which is able to convert electricity into something else, or, for example, if there were a component that would convert light back into electricity, that would also be a transducer. In particular, we call the LED in this particular situation an actuator, because it takes electricity and then turns into something that I can actually see in the real world. In this case, I can see the light. Electricity is invisible to me, but the LED makes electricity visible by turning it into light. We have our completed circuit, and I would like to make some modifications now to introduce some other concepts. So what we are looking at here is a very simple circuit where each component is connected to the next component in the circuit, and then the last connection goes back to G and D. So you can imagine the current flows from the red wire into the circuit, through the resistor, through the push button, then in this wire, then through this LED, another wire back to ground. So this is how the circuit is closed. One of the features of this circuit is that the elements, we say, are connected in series, because one component comes after the other. And we can make this circuit a little bit more complicated, because at the moment we have only one button. So what happens if I connect another button? So I can remove this jumper, and then I'm going to add another push button, making sure that it's connected with the LED. So now when I press these buttons, nothing happened, because the circuit is still open. We have to close the circuit using one of these wires. So I will plug the wire here, I will plug the other wire here, and if everything works out, I press the button and still nothing happens. Why? Because these two buttons are connected in series, so they are one after the other. If I want to operate the circuit, I need to press both buttons at the same time. So look at this. When I press button number 1 and button number 2, the current is able to flow through the circuit, and when I release one of the buttons, the circuit is open and it stops operating. So what we have learned now is that if we put buttons in series, so one after the other, I need to press all of them in order to close the circuit and make this electricity flow. Inside the push button, there are two pieces of metal that are separated by a spring. When you press the button, these two pieces of metal, they come in contact and they create an electrical connection and the electricity can flow through them. When you release the button, the spring pushes the two pieces of metal away and it interrupts the circuit, it opens the circuit. So you will notice that the push button has got 4 legs. At the moment we used only 2. What are the other 2 legs doing? Well, actually, they are internally connected to the first set of legs. So the 2 legs on this side of the push button are internally connected together, and the 2 legs on this side of the push button are internally connected together. So this increases the number of combinations that you can use when you create circuits. And so what happens is that if I take this jumper that I use to build this circuit, I can actually mount it behind the push buttons, and the circuit still works. So what you will notice is that this point in the circuit and this point in the circuit are exactly the same. And here, this point and this point are exactly the same. So when I press the button, these 2 points in the circuit are connected with these 2 points in the circuit. When I release the button, only these 2 points are connected and these 2 points are connected individually, but there's no connection between the 4 of them. So this allows me to try to create another connection that we call parallel connection. The idea is that we can actually place one button next to the other, and we can create 2 different paths that the current can use to actually flow through. Let's see what happens if we put these 2 push buttons in parallel. So what I'm going to do, I'm going to use 2 jumpers. So I'm going to connect one leg of the first push button with the same leg on the second push button, and I'm going to do the same for the remaining contact, 1 and 2. So what happens here is that if I press the button, now the LED comes on. And if I press the other button, the other LED comes on. And if I press both of them, the LED comes on at the same time. So what's happening here is that by creating 2 different paths for the current to flow through, I just need to press one of the 2 buttons for the current to reach the LED and light up. If you put the buttons in series, you need to press one button and the other button in order to create light. And in this particular configuration, you need to press one button or the other button in order to turn on the LED. So in a way, this small circuit is creating a very basic logic circuit. One that has an AND logic. You need to press one button and the other in order to light up the LED. And the second one is an OR circuit. You press one button or the other. That's all for today. I hope you enjoyed the tutorial, and remember, build it, hack it, share it, because Arduino is you. Hi, my name is Massimo Banzi, and I like to make stuff. So today we're here to look at another project from our Arduino starter kit. Today we're making the Spaceship Interface. This is a simple project designed to teach you about simple inputs and outputs with Arduino. This circuit is going to show you how simple it is to connect a small button and a set of LEDs to the Arduino board, and how you can control the LEDs through the button. First, I want to explain to you a few concepts about Arduino. First of all, Arduino, it's a small computer the size of a credit card, as you can see here, that we can program using the Arduino development environment. I'm going to show you in a few minutes. So the idea is that we write instructions in the development environment, then we press a button that gets turned into a program that gets downloaded into the Arduino, and then the Arduino can interface with the outside world to implement any crazy project that you can come up with. So this project is very simple. We have a button connected to pin number 2 on the Arduino, and then we have 3 LEDs connected to pin 5, 4, and 3 of the Arduino. When I press the button, these 2 LEDs that are now blinking will stop blinking, and the yellow LED will turn on. If I release the button, the 2 LEDs will keep blinking. So this is a very simple circuit that allows us to control the behavior of these 3 LEDs from this button. Let's have a look at the code that we need to implement this behavior. At the beginning of the code, we have this line that says const int red LED 1 equal 5. So this creates a constant called red LED 1 that contains the value 5. This is actually a very clever technique that allows us to give a meaningful name to pin numbers. So throughout the code, I don't have to use numbers, but I can use red LED 1 to remember that that particular pin is associated with the first red LED. And if you look, there are another couple of lines where you define a constant for red LED 2 and green LED. Then later on, we have another constant called switch pin equal to. This specifies that the switch or button that we're using is connected to pin number 2. Then let's look at the setup. The setup is that part in your Arduino code that gets executed once when the board is powered on or reset, or this means also right after you upload some code into the Arduino. And so as I said, this gets executed only once. So we see the instruction pin mode. Pin mode basically tells Arduino that we want to make sure that pins red LED 1, red LED 2, and green LED are all configured as output, because the input and output pins of the Arduino can be configured to assume both configurations. Then we have an instruction called pin mode, switch pin input, which is used to specify that the pin number 2 is connected to a switch, and then we want to make sure that that's an input so that we can read from it. Now, let's have a look at the loop section. The loop section in your code gets executed over and over as long as the board is powered on. So we create a variable called switch state, and then we say switch state equal digital read switch pin. So basically what this does, reads the state of the pin connected to the push button and returns the value high or low, depending on the fact that the button is pressed high or released low. Then we're going to use a clever statement called if, which is very important whenever you write some code, because it's the statement that allows you to make decisions. So in this particular case, we basically ask Arduino, if the switch state is equal low, do something. So in this case, we use the curly bracket to group lines of code together. So you can see that the if statement is followed by a question, a condition that needs to be verified, and then a curly bracket that specifies which lines of code need to be executed when the condition is true. In this case, switch state equal low basically says if the button is not pressed, and then we follow that with a series of digital write statements that are used to turn on and off the LEDs and to implement this particular blinking behavior. After that, we have a delay of 250 milliseconds, followed by a short blink cycle that happens on the other red LEDs. So the instructions that you see in this section of the if statement are used to implement this blinking behavior that you see here. Afterwards, there's a statement called else. Else is a statement that allows you to basically create a fork in the road in your Arduino code. With if, you can say, if something is true, execute this piece of code, and else says, if that condition is not true, then execute this other piece of code. So you can have two different parts of your code that gets executed depending on the condition, if that condition is true or false. In this case, when the button is pressed, then we use two digital write to turn off the red LEDs, and we use one digital write, green LED high, to turn on the green or yellow LED like we have here. So if I press the button, the LED turns on. If I release the button, the LEDs are blinking. So this is all the code that we need in order to implement this behavior. I want to remind you that the code that's inside the loop statement will be executed over and over. So as you can see, the blinking pattern is executed, then Arduino reads the input, checks if it's true or false, and depending on that, decide which behavior to implement, and then loops back to the beginning. That's all for today. I hope you enjoyed the tutorial, and remember, build it, hack it, share it, because Arduino is you. Hi, and welcome to another video about our Arduino starter kit. This is called the Lovometer. This project is used to measure how hot you really are. Actually, in simple words, this circuit is a very simple thermometer that measures your body temperature and visualizes it on a string of LEDs. So let's look at how the circuit is built. There are 5 LEDs on this circuit that are used as an output. So you can visualize the temperature by looking at the number of LEDs that are on at any given time. And so this is an extension to the previous project we looked at when we used 3 LEDs, and now we learn how to use more LEDs, so we go up to 5. But the more important part about this circuit is actually the sensing. In this particular circuit, we use a temperature sensor called TMP36. And the interesting feature about this sensor is that it's a very precise temperature sensor that generates a voltage which is proportional to the temperature that it measures. In particular, this sensor generates 10 millivolts of voltage for every degree centigrade plus 0.5 volts. So for example, if the temperature in this room is 20 degrees, then 20 multiplied by 10 millivolts is 0.2 volts plus 0.5 volts, which is the basic voltage that's always produced at 0 degree by the sensor. So when the temperature in this room is 20 degrees, the sensor will produce 0.7 volts. Now we hit an interesting problem. In this particular case, we were using a pin that was able to measure if the signal was on or off. Was it basically able to measure if there was or there wasn't any voltage applied to the input pin. In this particular case, the sensor is producing a voltage which changes depending on the temperature. So if we want to actually be able to measure the temperature, we need to be able to measure the voltage produced by the sensor. So the digital pin, it doesn't work here, because the digital pin basically says if the voltage is more or less 3 volts, then the input is high, and if the voltage is more or less 0, then the input is low. We need something that is going to able to give us a number which is proportional to the voltage that it's measuring. Here we introduce the analog inputs on the Arduino board. You can see here that there are 6 inputs on our circuit called analog in, and each one of them is able to measure a voltage between 0 and 5 volts, and it will return a number between 0 and 1023 proportional to the voltage it's measuring. So when the voltage is 0, it's going to be the number returned by analog, by the analog inputs is going to be 0. And when the voltage is 5, the number is going to be 1023. And for example, for 2.5 volts, the number returned by the input is going to be roughly 512. So what we are doing here, we wired up the sensor in a way that we are providing power, the connection to ground, so we're powering the sensor, and then the sensor has a third leg that we connect to analog input 0. So whenever the temperature changes, the voltage changes, the Arduino uses a new instructions that we're going to see in the code later on called analog read that will give us a number that we can use to calculate the actual temperature. Let's try the circuit for a second. I'm going to grab the temperature sensor and see what happens. So you can see now that the LED are turning on one after the other when I touch the sensor. And if I release the sensor now, the temperature is going to slowly go back down, and you will see the LEDs start to turn off one after the other. So now that we see that the circuit is working, we should be looking at the code and understand how we have implemented this functionality. So let's have a look at the code for this example. So if we look at the code, you see some familiar elements like the setup function. So let's start at the beginning. We define a constant called sensor pin that maps the analog input 0, A0, in the code here, you can see A0. And this one allows us to be able to change the input pin if we want to, and it gives a meaningful name to that particular input. So we know that the temperature sensor is connected there, so the code becomes more readable. Then in the setup function, the first thing that you see is that we are using serial.begin 9600. Basically, this is a new function that we have introduced in this example. It allows the Arduino board to communicate with your computer. So serial.begins opens a communication channel between your Arduino board and the computer. 9600 specifies the speed, 9600 bits per second. So this allows us, for example, to print numbers that we read from the analog inputs and send them to the computer, where we can use the serial monitor that I'll show you in a few seconds to visualize the data that comes from the Arduino. Then we find a for loop. The for loop is useful in order to execute a certain number of instructions for a very well-defined number of times. In this particular case, what we are doing, we need to turn 5 pins on the Arduino to become outputs, and we need to turn them off. So instead of writing the same 2 lines of code for 5 times, we use 4. If we look at the code, we see that 4 starts with x being equal to 2. Then every time that we execute pin mode and digital write, x increases by 1. X++ is the instruction that increases the value of x by 1. And we keep doing this until x is less than 5. So when we hit pin number 5, we stop doing this loop. So this is very useful if you have to apply the same operation to a number of pins. So let's delve now into the loop. Inside the loop, we are reading the sensor value using analog read. So we have sensor val equal analog read sensor pin. This will measure the voltage and return an integer number which is proportional to the voltage that's been read. Serial.print prints the number towards the computer, and serial.print ADC specifies that the number that we just sent to the computer is the raw value from the analog to digital converter. The analog to digital converter is the circuit inside the Arduino processor that turns voltage into numbers that we can use in our code. So the next operation turns the number read by the analog to digital converter into the actual voltage. So we specified that the numbers between 0 and 1023 represent the voltages between 0 and 5 volts. So what we are doing here, we are dividing sensor val by 1024, which is the maximum, the number of values that are representable by analog read, and then we multiply that by 5. So this float type of variable is a new type of variable that we introduced with this example, that is able to store decimal numbers that in this case, it's needed because we're going to get voltages like 0.7, 0.8, so we need to be able to represent these kind of numbers. Then we follow that with serial.print voltage and serial.print volts, This, again, sends to the computer the voltage computed by the Arduino and the string volts to specify that the previous number was the amount of voltage. Now here is where we actually make the calculation of the degrees. The sensor, as we said, is producing 10 millivolts per degree centigrade and then adds 0.5 volts to all the values. So if we look at the code, we are taking the voltage, we subtract 0.5 volts, and we multiply by 100. Using this formula, we convert the voltage measured by the Arduino into the actual temperature in degrees centigrade. Then we print the temperature, and then we use a new function called println to write the string degrees centigrade. Println, on top of sending the information back to the computer, sends this new line special character that tells the serial monitor on the Arduino to start printing the next line at the beginning of a new line. So this makes sure that all our values that we visualize are all nicely aligned and readable. Finally, once we have the temperature, we need to be able to decide how many LEDs are turned on and off depending on each temperature. So what are we going to do? Actually, we're going to use a series of ifs. In the previous example, we used if-else to be able to decide to execute one part of the code or another part of the code depending on the result of a question, of a kind of a condition that we ask Arduino to verify. In this particular case, we have to verify multiple questions because we have 5 LEDs, therefore we have multiple combinations. So we use a different kind of if combination called else if. So we ask Arduino, is the temperature less than the baseline temperature? If that's true, Arduino is going to turn off all the LEDs. If the temperature is in the first band, we have an if that's measuring if a temperature is more than a certain value but still less than another value. If the temperature is within that band, one LED will be turned on. And then we have another else if that basically goes through every combination of value until we are able to turn on all of the LEDs. So in this particular code that we are displaying here, we are using if-else, else-if, to divide the temperature range that we want to measure into bands. And then we check to see in which band the temperature falls in. And we decide which LEDs to turn on and which LEDs to turn off. Then, through the last else-if, we basically reach the end of the program. Then the loop is going to start again, and we're going to go through the same sequence. Measure the temperature through analog read, take the number, turn it into a voltage, then from the voltage compute the temperature, print all of that information onto the screen, and then afterwards decide which LEDs to turn on depending on the temperature. So if now I grab the sensor, the temperature increases, and the if statements are deciding which LEDs. For example, at the moment, this LED is flickering because the temperature is across 2 bands, so it's still undecided which one should be turned on. If I release this, and maybe I blow a little on the circuit, you will see that this LED will start to flicker a little bit and then turn off. So we're now reached the end of this example. We have learned a little bit more. We've learned about controlling multiple LEDs. We learned about reading analog inputs, converting the values into voltages, converting the values into temperature, using multiple if statements to divide values into bands and make multiple decisions, and then how to print all this information back to the computer. I hope that you will enjoy playing with this project, and I'll see you in the next video. Hi, I am Massimo Banzi and I like to make things. And welcome to another Arduino tutorial video. Today we're going to be building a Theremin. The Theremin is a musical instrument that produces different sounds depending on the position of the hands of the player around the instrument. In this particular case, we're going to be building a very simple Theremin using a light sensor as a way to capture the position of the hand of the player from the Arduino. You'll be using a photoresistor to detect the amount of light, and from the amount of light we are going to guess the distance of the player's hand from the sensor. So here we have a piezo buzzer. The piezo buzzer produces sounds every time it's turned on and off. So, and it's connected with the wire to pin number 8. While here we have a light sensor connected to analog input 0. So the light sensor detects the amount of light that hits the surface of the sensor. So by moving the hand from the sensor, we reduce or increase the amount of light that hits the sensor, and in turn, this information goes into the Arduino as a variation of voltage. In our code, we're going to use the variation of voltage to gauge the distance of the player's hand from the sensor, and we're going to map that to the appropriate values of sounds, and then we're going to drive the piezo capsule using the tone function in Arduino. Let's start building the circuit. The first thing to do is to connect the power bus with a red and black wire to the two strips on the side of the breadboard. Then we connect the piezo buzzer. Since the piezo buzzer is a bit tricky to mount, we have to prepare the two wires at the right distance on the breadboard and then plug in the piezo in the correct lines on the breadboard. Now let's place the photoresistor. Here is the photoresistor. We place it on the breadboard. We connect a resistor between this leg of the photoresistor and ground. Then we have another wire going from the 5-volt rail to the other side of the photoresistor. And then one wire connects the photoresistor and the resistor here to the analog input 0 of the Arduino. So in this case, we have set up a sensor that reads the amount of light and converts that into voltage that we can measure with Arduino. And then we have connected an actuator, the piezo capsule, that produces sounds. And now we're going to write a piece of software that ties them together. The software that we're going to be using with this project starts off with a 5-second calibration period. So during this time, you will move your hand near the sensor like this to let the Arduino calibrate the values that represent the minimum and the maximum amount of light that can hit the sensor. After those 5 seconds, Arduino will start the main loop. And during the main loop, we have a very simple structure. We read the amount of light in terms of voltage applied to the analog in, and then we convert that to a suitable frequency to play on the piezo speaker. And then we use the tone function in order to play that sound. Let's look at the code. We start off at the beginning, defining a few variables. The first one is called sensor value. It's an integer variable that stores the values read from the light sensor. After that, we define two variables called sensor low and sensor high, and these are used in the calibration phase to determine which one was the minimum and the maximum value read from the sensor. So where's the trick? As you can see, we are defining the variables. Sensor low starts off as 1023, and sensor high starts off with 0. This is done on purpose to make sure that if we read a value from the sensor, it will always be less than 1023. So if we start with sensor low at 1023, we'd make sure that the first value that we read will be less and the calibration can operate correctly. At the same time, we are using sensor high and setting it up at 0 so that any value that we read from the sensor will hopefully be more than 0. After these variables, we define the classic constant LED pin, and we assign 13 because we're going to use the LED to signal when the calibration phase is over. In the setup, we have pin mode, defining pin number 13 as an output. And then we digital write onto LED pin high, so we basically turn on the LED to signal that the calibration phase has begun. Then here, we have an interesting piece of code. It's a while loop that uses the millis function to make sure that the calibration phase lasts for exactly 5 seconds. So how's that done? So the millis function is a function that returns the number of milliseconds that have passed since the last time that the Arduino board was turned on or reset. So every time you upload code, or you press the reset button, or you plug the power, the Arduino starts from 0 milliseconds, and millis will return a number that grows as time goes by. What we're going to do here is that since this code is exactly at the beginning of the setup, it's happening in a very few milliseconds right after the board was turned on. So by doing while millis less than 5,000 that we have here in the while loop, we make sure that the code within the while loop is executed only during the first 5 seconds that the board has been turned on or reset. So what is happening here? So we read, through analog read, we read input 0, we place that into sensor value, and then with a very simple algorithm, we check if sensor value is more than sensor high, then we make sensor high equal to sensor value. So essentially, we are saying, is the value that I'm reading from the sensor right now higher than the highest value I have read until now? If that's the case, then that value becomes the highest value that we have read until now. The same thing we do for sensor value and sensor low. So again, we check if sensor value is less than sensor low, then sensor low becomes equal to sensor value. This code gets executed as many times as possible within the 5 seconds after the board was turned on or reset. So if I move my hand on the sensor like this during the first 5 seconds that the program has started, I basically let the light sensor experience all the possible values of minimum and maximum light. And after that, I come out of this calibration phase with the maximum and the minimum value stored in sensor low and sensor high. Then you can see here with digital write LED pin low, we are turning off the LED to signal that the calibration phase is over. And then the loop is very simple. During the loop, we read the analog input 0 and we store that into sensor value. Then we are going to use an interesting function called map, because we have a minimum and a maximum value that the sensor can read in the current light conditions. And then we have the minimum and maximum audio frequency that we want to play back. So instead of having to calculate manually the matching between those values and the frequency value that we want to play back on the piezo speaker, then what we're going to do, we're going to use this function called map. Map is very simple to use. We specify a value that we want to map. The first parameter is sensor value. Then 2 parameters follow sensor value. They determine which is the value range that the input value can have. So sensor low and sensor high determine this is the range of values that sensor value can assume. The last 2 parameters of the map function, they determine which is the output range that we expect from map. So very simply, we say, this is a value. This value can be between a minimum and a maximum value, and depending on which value I am processing, I want to produce a value which is within this other range. So our aim is to basically say, for any value within sensor low and sensor high, we have to produce a number between 50 and 4,000 that represents the frequency of the audio signal we want to produce. The result of this calculation goes into the pitch variable. In the next line of code, you can see that tone is producing a sound on the piezo speaker connected to pin number 8, and the pitch is the value that we calculated previously using map, and then 20 is the duration of this sound. After this sound has been produced, we delay for 10 milliseconds, and then we continue. So now let's upload the code onto the board and see what happens. You can see that if you gauge your movement properly, you can produce a lot of different sounds. I'm sure you will find this project funny, probably for the first 5 minutes. Then the sound will become too annoying and you will be prompted to do this. So thank you for listening. So now you have to build it, hack it, and share it, because remember that Arduino is you. Hi, I'm Massimo Banzi and I like to make stuff. Welcome to another tutorial taken from our Arduino starter kit. So today we're going to be building a small musical instrument. You can see here it's again a simple circuit. We have 4 buttons connected to the Arduino and a small piezo speaker or piezo speaker, depending on where you come from. So let's press the buttons and see what happens. So each button is associated with a note. So every time I press a button, Arduino produces a sound through the piezo speaker. So how does this work? Well, let's start from the circuit. You can see here there are 4 buttons, but the 4 buttons are connected to the Arduino board with just one wire. So in the previous examples, we've seen that for every button, we had a wire going to the Arduino board. We were using one digital pin to read each individual button. And here we have 4 buttons connected to just one wire because we have built what is called a resistor ladder. So there's a combination of resistors and buttons. And when I press one of the buttons, I create a combination of resistors that let the current flow through them, but then the voltage that the Arduino board measures out of this resistor ladder changes depending on which button I press. So each combination of buttons produces a different voltage. And you know that voltage applied to an analog input can be read from the Arduino using analog read, and then using a series of if statements, we can actually say, okay, if the value is between this number and this number, I press the first button. If it is between another set of numbers, I've pressed the second button. And I can experimentally figure out which one are the buttons that I've pressed by looking at all the numbers that come out when I press the different buttons that correspond to the combinations of resistors. Now, the output of this circuit, the actuator, is this piezo speaker. The piezo speaker is a very simple device made of piezoelectric material that has this feature that whenever you power it with electricity, it will make a small click. If you turn on and off the power to the piezo speaker at a certain speed, this sequence of clicks make a sound. So for example, if I turn on and off the power 440 times per second, I produce a sound which is a very well defined note. So in our code, as we will see in a few minutes, we have defined all the different frequencies of each note. And when you press the button, the Arduino detects which button has been pressed and then plays that particular note on the speaker. So now let's have a look at the code and let's read it line by line to understand exactly how to implement this behavior. Let's start from the beginning. You can see on this line that we are defining a new type of variable called an array. So this is a variable called notes that contains 4 different integer values. Each one of these integer value represents the frequency associated to a certain note. In particular, these are the middle C, D, E, and F notes. This will be useful later. When we detect which button has been pressed, we can then choose the right frequency to play on the speaker. Then we have the usual setup where we have a serial begin to begin a communication with the computer. So let's look at the loop now. The first thing we do, we create a variable called sounder that contains the value read from the analog input 0. That represents the combination of keys that have been pressed on the keyboard. Then we print that value on the serial monitor so that we can look at it on the computer. And then we start to understand which button has been pressed. So we do this by looking at the sounder variable using a set of if and else if statements to segment the value in different bands and which figure out in which band the value falls, and each one of them corresponds to a sound. So at the beginning, when the value is 1023, then we know that we have to play the middle C. We are using a new function called tone. Tone is able to produce a sound on a small speaker or piezo speaker connected to a certain pin on the Arduino. The only thing we need to do is we need to say this is the pin where the speaker is connected to, in our case number 8, and then we have to specify the note, and that note will be played on that pin. Then if we continue down the source code, you can see that there's a number of else-if statements that divide the value of sounder in different bands. So we have a band that goes between 920 and 1010, that corresponds to the middle D, a band that goes between 505 and 515 that corresponds to the middle E, and finally, a band that goes between 5 and 10 that represent the middle F. If none of this combination is actually detected, then there's a final else statement that you can see here. This else statement calls this function called noTone that stops any sound being produced on a specific pin. So we say noTone 8, and this stops the sound. So let's try again the instrument and see how our software is actually working here. In the same time, I will open my serial monitor so that we can see the numbers while I press the button. So at the moment, we see a value which is very close to 0, which represents the fact that no button has been pressed. So we press a button, and we get 1023. The second button is 1002. The third button is about 512 or something. And the last one is kind of in that sort of 15, 20 sort of value. So this is, in a very simple way, a small musical instrument that you can build very quickly with your Arduino, a piezo speaker, a few resistors, and a few buttons. So this is all for now, but remember, build it, hack it, share it, because Arduino is you. Hi, my name is Massimo Banzi and I like to make stuff. Welcome to another Arduino tutorial video. Today, we're going to be learning how to use Arduino to move things in the real world. To do that, we need to learn how to control a DC motor using Arduino. So the DC motor is a simple electromechanical device that you see here that it's normally powered by a 9-volt battery. And we're going to be building a circuit that lets Arduino turn on and off this motor, and we'll be using that to control this color wheel that we have manufactured using an old CD. So in the kit, you will find parts in order to build the wheel adapter, and you will find a paper that you can glue on top of the CD. So what are the issues that we have to take care of? Well, first of all, the DC motor here works normally at more than 5 volts, which is the standard voltage that the Arduino operates at, and requires more current than a single Arduino pin can provide. Normally, we can just hook up a regular LED to an Arduino pin because the amount of electrical current that the LED needs in order to operate is low enough that you can power it with an Arduino pin. But in the case of the DC motor requires a current which is much higher, and we risk burning the Arduino pin if we try to hook it up directly. There's also another issue that we have to be aware of, is that when you turn on and off a motor, an electrical motor, when you turn it off, actually, it generates a spike of negative voltage that can actually go back into your equipment and destroy some of the parts. So in order to solve this problem, we are going to use a new component that we haven't used in the other videos, which is called the MOSFET transistor. This is essentially a switch that can be turned on and off by applying or not a voltage to a certain pin of the MOSFET transistor. So the MOSFET here has 3 pins called source, drain, and gate. The power MOSFET is essentially an electronic switch that can be turned on or off by applying a voltage on a pin called the gate. So this MOSFET transistor has 3 pins called gate, source, and drain. So if you apply a voltage to the gate pin, it connects the gate and the source together, like I was pressing a button on a switch, but this is all done electronically. So I can use this to connect the battery to the motor, and since the MOSFET is sitting in between, it basically connects and disconnects the motor from the battery, and I can control this through software that I write on the Arduino board. When you turn off an electric motor, it normally generates a spike of negative voltage that can actually destroy your equipment. So even if the MOSFET is quite strong, it's still very sensitive to these negative spikes of voltage. So we have added to the circuit this flywheel diode, it's called, that basically conducts only when the motor generates these dangerous spikes of voltage and protects the MOSFET from burning. So what the MOSFET is doing for us, it lets us control loads that are larger than we can normally do with an Arduino pin. It lets us operate at a voltage which is higher than the standard Arduino voltage. So as I said, Arduino operates at 5 volts, but with the battery here it's 9 volts. So using the MOSFET allows us to switch on and off bigger loads that operates at voltages that are higher than the Arduino standard operating voltage. It protects us because if something happens, the MOSFET blows up at worst. But using the diode, the way we hooked it up here, we can actually protect the MOSFET, and we have a fairly reliable and robust way to turn on and off, but even change the speed if we want of this DC motor. So let's look at how we can build this circuit. First of all, we place the MOSFET on the breadboard, and then we connect the negative, the black wire of the motor right in the middle pin. Then, if you look at the MOSFET from the front, where you can see the markings on the front, then the pin on the left-hand side, that's the gate. So we're going to wire it up to pin number 9 on your Arduino. And then the pin on the right-hand side, that's the ground. So we're going to connect it with the jumper wire to the ground rail here on the breadboard. Then we're going to connect the ground from the battery together with the ground on the breadboard, so that the battery and the Arduino have got the ground in common. This is a condition needed so that the power supply on the Arduino and the battery have got the ground in common, so the voltages are all referring to the same ground, and the circuit can operate properly. The circuit works like this. We connect the 9 volt coming from the battery directly to the motor, and then from the motor we connect the ground pin of the motor to the MOSFET, and then the MOSFET connects to the actual ground on the circuit. So when the Arduino pin turns on and off, a 5 volts voltage will be applied on the gate. When the gate receives the voltage from the Arduino pin, it will connect the motor to ground, and the motor will start to spin. When we remove the voltage from the gate pin, the MOSFET will open and the circuit will break and the motor will stop running. Let's look at the sensor part of the circuit. In our case, the sensor is a button. So we wire up the circuit in the usual way. We have a button here. We have the resistor, which is a pull-down resistor. So we connect power to the button to resistor, resistor to ground, and the point where the button and the resistor connect is where we connect a wire to take that voltage and bring it to pin number 2 on the Arduino. So every time I press the button, the Arduino detects that condition and turns on the MOSFET. So here we have a motor, and there's a small adapter that adapts the motor shaft with this pinwheel that we manufactured using an old CD and a piece of paper that you can find in the kit. So once I created the adapter, I'm going to put a little bit of glue on it so that the CD is not going to fly away the moment I turn on the motor. So let's put a few drops of glue. Let's try. You see now that it's picking up speed, and it's turning into this interesting cappuccino color. And if I release the button, the motor starts to slow down. That's pretty good. Okay, so this was our example, and now let's have a look at the code. So starting from the beginning, we have a couple of constants. Switch pin, which maps the switch to pin number 2, and motor pin, that maps the motor onto pin number 9. And then we have a variable called switch state equals 0, which will contain the state of the push button, and it will be used in an if statement to determine if the motor has to be on or off. Then let's look at the setup. In the setup, we have pin mode, motor pin output. So that defines that the pin that connects to the MOSFET and controls the motor is an output. And pin mode, switch pin input, that basically says that the pin connecting to the push button, it's an input. Then let's now look at the loop. Inside the loop, we begin by reading the state of the button by saying switch state equal digital read switch pin. So this reads the current state of the button and then places high or low inside the switch state variable. After that, we have an if statement. If switch state equal high, so if the button is pressed, digital write, motor pin high, so that turns on the motor. Else, digital write, motor pin low. And this if statement looks at the state of the button. If the button is pressed, we turn on the pin. If the button is released, we turn off the pin. When the pin is on, the MOSFET connects and starts the motor. This is all the code that's needed to build this simple application. Now, you can hack the software and add more functionality. For example, if you look online, you may be able to find some code that teaches you how to turn on and off the motor when you press, or if you press again, it turns off. So in order to operate that toggle switch, or you can learn how to change the speed of the motor. So the number of things you can do now with this project are a lot. If you remember to build it, hack it, and then share it, because Arduino is you. Hi, my name is Massimo Banzi, and I like to make things. Welcome to another Arduino tutorial video. Today, we're going to build an electronic version of the Magic 8 Ball. So this is a simple device with an LCD screen that provides a different answer every time it's being shaken. So let's try. Look at this. 8 Ball says Outlook good. So how does this project all work? We have a sensor, which is the tilt sensor over here, that contains a small ball sitting on two contacts. When the tilt sensor is vertical, the ball sits on the contacts, closes the circuit, and acts like a push button that's being pressed. When you shake the board, the ball bounces off the contacts and opens the circuits, and it's almost like it's like when you release your finger from a button. The data from the sensor goes into the Arduino, and there's a software that detects that you're shaking the Arduino and picks a random answer and displays it on this LCD display. It's fairly simple to connect an LCD screen to Arduino, and this one in particular because it's a character-based LCD. So it contains already electronics on the LCD module itself that can receive data from the Arduino in terms of character codes, and then display the characters on the LCD screen in the right position. Let's have a look at the circuit. So we have the LCD module here. We are bringing 4 wires from 4 Arduino pins to the LCD modules. Those 4 wires carry the data from the Arduino to the LCD screen. Then we have an extra 2 pins connected to the Arduino board that are used in the communication between the Arduino and the LCD screen. Then we power the LCD screen. You see there's a red and a black wire coming from the plus and minus rail. Then there is this potentiometer. The potentiometer here is used to generate a voltage between 0 and 5 volts that is applied to the contrast pin. So if I start turning this potentiometer, you can see that the contrast on the display changes. So we have to tweak it until the value makes the display work properly. So this can be tweaked depending also on the angle that you watch the LCD. So as I said, data, a couple of control lines, power, contrast, and this is all we need in order to connect to the LCD module. Here we have the tilt sensor is wired up exactly like a regular push button. So we have one leg of the tilt sensor is connected to a resistor to ground, the other one is connected to 5 volts, and the place where the resistor and the tilt sensor connect is where we connect a wire that goes to an input on the Arduino board. Then the Arduino can read if the tilt sensor is connected or not. So when I shake, like this, Arduino detects the shaking and changes the answer on the screen. So to recap, we have a tilt sensor connected to the Arduino, and we have 6 wires coming from the Arduino and connecting to the LCD screen. The data that goes from the Arduino to the LCD screen is actually represented as 8-bit numbers, but we wire up only 4 wires, and we use a special mode in the LCD displays that carries 8-bit data at 4 bits at a time. So using the LCD would require you to write quite a lot of code, but luckily there is a liquid crystal library inside the Arduino platform that allows you to control this class of character LCD displays in a very simple way. So now we're going to have a look at the code, and we're going to figure out how everything works. Let's look at the code. We start by including the liquid crystal library. So we use #include liquidcrystal.h. This can be done actually by selecting appropriate import library menu from the IDE. And then once we have included the liquid crystal library into our code, we have to tell the library which one are the pins that are connected to the LCD. So we specify 12, 11, 5, 4, 3, and 2. These are the pins that we're using here to convey the 4 pins of data, then the RS and RW pins that are used in the handshaking and in the communication between the Arduino and the LCD. Once we have done that, we are ready to use the LCD screen. So we define another constant, switch pin equals 6. This switch pin, this pin number 6, is where we connect the tilt sensor. Switch state, again, is a variable used to store the current state of the tilt switch. And then we have another variable called pre-switch state. And the fact that we need to store the current and the previous value of a certain switch will become clear later. Then we have another integer variable called reply. So let's look at the setup function. We open the communication with the LCD screen by using lcd.begin. And then in the begin function, we specify 16 and 2 to tell the library that the LCD that we are using has 2 lines of 16 characters each, because there are many different types of LCD screens like this. So when we initialize the communication, we have to specify the size of the LCD display. Then we use pin mode to tell Arduino that switch pin is an input. And then we use lcd.print to write the first line at the top that says ask the. Then we use another interesting function of the LCD library, lcd.setCursor. SetCursor allows us to specify which column and row we want to start printing from. So I can move the cursor anywhere on the LCD display by specifying the position. With the last line in the setup, we print the second line on the screen. So lcd.print magic 8 ball. So to recap, in the setup, we're basically opening the communication with the LCD screen, preparing the pin, a switch pin to be an input, and then we print on the 2 lines of the display, ask the magic 8 ball. Then let's get into the loop. So the first line in the loop stores the current state of the switch into switch state by doing a digital read on the pin. And then we say, if switch state is different than previous switch state, and this if statement It's used to figure out if the state of the button has recently changed, because we want to provide a new answer on the screen only when the state of the switch changes. And the state of the switch changes only when I shake the circuit and the ball inside the tilt switch jumps up and down. So if switch state and previous switch state are different, then we can move on and we can say, if switch state equal low, then actually generate a new reply. So we start from clearing the display by using lcd.clear. Then we generate a random number between 0 and 7 that gets stored into the reply variable. Then we set the cursor to 0, 0, so the top left corner of the screen. We say, we do LCD print 8 ball says. Then we set the cursor on the second line of the display by doing LCD set cursor 0, 1. And then we use an instruction called switch that basically allows us to run different parts of code depending on the value of a specific variable. In this case, we switch based on the value of the reply variable. So if the number that was generated randomly is 0, we are going to lcd.print on the screen the word yes. And then we have a statement called break that tells Arduino that we're done executing the code in that section and we want to exit the switch statement. And then for every particular value that the variable can assume, we have 0, 1, 2, 3, and each one of them corresponds to a message. So we have unsure, ask again, outlook good, no. Once we are done going through the switch statement, the screen will have an answer. And then at the very bottom of the code, we have one line that says prev switch state equals switch state. So the current state of the switch state is not current anymore. At the end of your code, that's old. It's the previous state. So we store it in previous state, and we go back to the beginning, where the first line is taking a new value into switch state. And this allows us to detect every time the value changes. We got to the end of the code, and this is the end result. So I'm going to press the reset button so we can start the code from the beginning. So you see, ask the magic 8 ball. So I'm going to shake this, and the magic 8 ball says yes. So I have to ask a question. Was this video cool? Yes. The magic 8 ball says yes. So I think this is a very good conclusion for this video. I hope you enjoyed the video. And remember, you have to build this tutorial, you have to hack it, and you have to share the results on the internet, because Arduino is you. Hi, my name is Massimo Banzi, and I'm one of the co-founders of the Arduino project. And we're here for another video about our Arduino starter kit. Today, we're going to look at the new project called the touch sensor lamp. This is a simple circuit where we're going to build a sensor that is able to detect when a human being is touching the circuit. You can see that if I touch this wire, the LED turns on. For this tutorial, we're going to introduce a new concept from the Arduino platform, external libraries. This is a very powerful concept because there are some things in Arduino programming that are very complex for a beginner. Like, for example, in this case, we are building a touch sensor. The touch sensor uses a fairly complex process for a beginner, and it would be quite complex for a beginner to write the code completely by themselves. So somebody with a lot of skills in Arduino programming developed a library that is able to perform this sensing function. On the Arduino website, you're going to find all the instructions you need in order to install a new library into the Arduino development environment. But let's have a look at this circuit. Here, we have an LED connected to pin number 12 of the Arduino. And then we have this strange circuit where we have a resistor connected between pin 2 and 4 of our Arduino. And then there's a wire connected to pin number 2. If I touch the wire with my finger, the LED turns on. So this is due to the capacitive sensor implemented by the library that we are going to see in a few seconds. The capacitive sensor is able to detect when a human being is touching a metallic surface. It's the same principle used by the touch sensor on the screen of every iPhone or Android mobile phones that you might have used. We can also increase the sensitivity of the sensor by using an external metallic surface. So I'm going to use a piece of printed circuit board that hasn't been etched yet. So as you can see, it is a piece of fiberglass with some copper on top. So we're going to connect this to my circuit and see what happens if I place a bigger surface. So we're going to help ourselves using this alligator clip. I'm going to connect the alligator clip to the wire and then to the copper surface. So now when my hand touches the surface, it turns on and off. Actually, what happens is that I don't even actually have to touch the surface. It starts to sense my hand even when the hand is just closed. Actually, if we flip the board around, here we have an insulating surface made of fiberglass, and still, if I place my full hand on it, it can still detect my hand. So the capacitive sensor is very useful because I can actually detect the touch of a person even through certain insulating materials. Now let's have a look at the code. Here you can see something new already at the beginning of the code. We are using this statement called include. You have this pound sign followed by include and capsense.h. So this statement tells Arduino to look for a library called capsense and include that into our program. As I said before, this is quite useful because it's going to introduce a piece of code which is quite complex and is going to make your life very simple. And you can find online literally hundreds of libraries that encapsulate the functionality of very complex sensors and provide you a very simple way to use them. So they are an incredibly powerful part of the Arduino platform. So a little further down in the code, you can see that we are creating an object of type capsense, and this object is called capsensor, and we are specifying that pin 4 and 2 are the two pins connected to the resistor, and pin number 2 is actually the one that goes to the sensor. So later on, we create another variable called threshold that is set to value 1000. This value will need to be determined experimentally while you work on your code. And finally, we create a constant called LED pin connected that specifies that the LED is connected to pin number 12. In the setup, you'll see there's nothing complex. There's a serial.begin that opens a communication channel with the computer at 9600 bits per second, followed by a pin mode LED pin output that makes sure that the pin connected to the LED is set as an output so that we can turn it on and off. If we look at the setup, we can see that there is an interesting command here. We're using the capsense library to read from the sensor, and the number 30 between brackets here is indicating that we want to read the 30 samples from the sensor. This makes sure that we filter out any unwanted noise or false reading. The value read by the sensor goes into this variable called sensor value. Later on, we print sensor value towards the computer so we can visualize it with a serial monitor. After that comes the moment where we have to actually decide if the LED has to be on or off. If sensor value is more than the threshold, then we turn on the LED. If sensor value is less, then the LED turns off. Then we introduce a small 10 milliseconds delay to make sure that we're not reading too fast. And afterwards, we just go back to the beginning of the loop, we read the sensor again, and we continue like this. If we switch on the serial monitor, we can actually see a series of numbers coming from the sensor. You can see that when I approach with my hand the PCB I connected to the sensor, the numbers increase. And when the number is bigger than a certain value that we set, which is 1000 in this case, when the value is more than 1000, the LED turns on. So this sensor can also be used as a proximity sensor if properly configured. Okay, so we are at the end of the tutorial. I hope you enjoyed this project, and see you later, alligator. Hi, my name is Massimo Banzi and I like to make things. And welcome to another Arduino tutorial video. Today we're going to learn how Arduino can control software running on your computer. So we're going to be using a very simple circuit that you can see here, where we're going to be reading the position of a potentiometer and sending that data over the USB connection into your computer, where a small program written in the processing language is going to be used to change the color of the Arduino logo depending on the position of the potentiometer. So how does this work? Well, if you notice, the Arduino has two chips. One main processor here, which is the one that executes the code that you program in the Arduino IDE, and this other smaller square chip that lets the Arduino processor communicate with the USB bus over to the computer. So we're going to be using, for this project, something that's called serial communication, because the Arduino will send data over to the computer 1 bit at a time at a certain speed that we will define in software, and then the square chip that you see here will convert that into USB data that travels over to the computer. We have used serial communication in the past in order to visualize the data that comes from the Arduino board within the Arduino IDE. There is a button on the Arduino IDE called Serial Monitor. If you press that, a small window opens up, and then you can see all the data that comes from the Arduino board visualized scrolling down the small window. And then there is a little menu at the bottom that says normally 9600, and that's, for example, the speed of communication used by the Arduino to send the data. So the Arduino speed of sending and the Arduino speed and the Arduino IDE speed of receiving have to be the same in order to sort of keep the data readable. So in this case, we're going to be doing more with the data that comes into the computer. Instead of just visualizing it on the screen, we're going to be using another software to capture that data and use it to do something and control the software from the Arduino. To do this, we're going to be using the processing language. Processing is that was a major inspiration and one of the bases for developing Arduino. And it's a great way to learn how to program. You can download the Processing IDE for free from the processing.org website. After you download it, you should install it according to the instruction you find on the website, and you should go through a couple of tutorials like the overview tutorial. After that, you can load the processing code into the Processing IDE, and you can load the Arduino code into the Arduino IDE, and then transfer the program onto the Arduino board. And after the code is loaded, you will see that the TX LED will start to blink, signaling that the Arduino is sending data. So you can open the serial monitor, see the data scroll on the screen. After you see that, the Arduino part of the work is done. You can close the serial monitor. Then you switch over to the processing IDE. You press the button to start the code on the processing IDE. That will read the data coming from the Arduino, from the serial port, and then you will use the number to change the background color of the Arduino logo. Now, we should go through the code and see in detail how the two different applications work. Let's build the circuit first. So here, you can see that we have a potentiometer plugged into the breadboard, and we have one wire going from the potentiometer to the analog input 0 in order to read the value coming from the potentiometer. Then we have two wires connected to the potentiometer going to the plus and minus rail on the breadboard. And then we have a red and black wire going from those two rails to the 5-volt and ground signals on the breadboard. So when I change the position of the potentiometer, a corresponding voltage is coming out of this wire and going into the analog input 0, and that data gets converted into a number that gets sent down to the USB cable over to the computer and then to the processing code. We'll start with the Arduino code. So here, you see the code is very simple. In the setup function, we have a serial.begin command with 9600 as a parameter. So this opens up the serial communication between the Arduino and the computer at the speed of 9600 bits per second. Then, in the main loop, we read from the analog input 0 using analog read A0. The value that we read is between 0 and 1023, and we divide that by 4. This is because serial.write, which is the function that we are using to send the data over to the computer, only accepts bytes that have a value that goes between 0 and 255 as a maximum value. So by dividing the result of analog read by 4, we go from a value that goes between 0 and 1023 to a value that goes between 0 and 255. So serial write sends the data from the Arduino onto the cable over to the computer. After that, we have a delay of 33 milliseconds just to avoid overloading the serial communication with too much data that can actually create some problem on some slower computers. So once the data is reaching the computer, then we have to explore what the processing code is doing in order to read that data and visualize it. So switching over to the processing code, at the beginning we have this import statement that imports the library called processing.serial. This one is the twin library of our serial.begin, sort of a serial library on Arduino. There is a corresponding serial library in processing that we are using to open the communication and read the data from the board. Then we have an object called serial that defines the serial port we want to use to communicate with Arduino. And then we define a p-image object called logo that will contain the logo image that we want to tweak. Finally, we have an integer value called bgcolor that starts off as 0 that defines the color of the background. So let's look at the setup function. At the beginning, we use color mode HSBC to define that the colors that we're going to specify later are using this HSBC convention. And you can read more about this in the processing documentation. Then we use the load image function to load the logo.png file into the logo object. Then the size function defines that the size of the processing output window is going to be the same as the size of the Arduino logo. Then here, there's a tricky part. There is a println statement that will print the list of all the serial ports that are present on your computer. This is because we need to know the name of the serial port in order to open the correct one. Now, for a strange number of reasons, on Mac, the Arduino board port is always the first one in the list. So if you look at the code that we have here, my port is defined as a new serial object that picks the element 0 in the list of ports, so the first port in the list. So on Mac and Linux, this generally just works out of the box. While on Windows, we get a list of COM1, COM5, COM3, COM19. The actual COM ports that you get on your computer change depending on your computer, where the Arduino is plugged in, and a number of other factors. So you will have to use the output of serial.list and what you see at the bottom of the screen on processing to determine which one is the port that you need to use. And then you change in your code, you change the 0 here that I am highlighting with the number of the port from the list that corresponds to your Arduino. After you're done that, the processing code is configured in order to talk to the Arduino, and we can then look at what happens in the loop. In the loop, we start off by setting the background to white by doing background 255. That sort of cleans the window at the beginning of each frame. Then there is an if statement that says, if my port.available more than 0, this basically is used by processing to check if that particular serial port has data that has come in recently that can be processed. If available returns a number that's larger than 0, there is data available that we can read. So we say BG color, which is the variable that defines the color of the background, equal myPort.read. So you can see now that if by looking at the code side by side, on the Arduino side, we have serial.write that sends the data. And then on the processing side, we have myPort.read that read the same number into the BG color variable. After reading the value that comes from the Arduino into the BG color variable, we use println BG color to print the value contained inside BG color at the bottom of the processing IDE window. After that, we use this function called background, where we use the value of BG color to define the hue of the color that we're going to use behind the Arduino logo. And then finally, by saying image logo, 0, 0, we tell processing that we want to basically overlay the Arduino logo on top of everything else on the screen, starting from coordinate 0, 0, so the top left corner of the window. If I now run the processing code by pressing on the Run button, I get a small window, and you can see that at the moment the color of the logo is light blue, and there is 128 being printed at the bottom of the processing IDE. If I move the potentiometer, you can see that each value corresponds to a color. So 0 is red here, then it becomes orange, then 71 represents green, for example, and then we get to blue, and then to purple, and back to red. So we have seen that we are able to capture the value of a sensor here on the Arduino board, convert that into a number that gets sent over the USB connection to the computer, and then there's a piece of software on the computer that can capture that number and use it to control something that happens on your computer. So now, this new thing that you learned today opens up a huge amount of possibility, because there are literally dozens of softwares on your computer that can actually read data from the serial port. So anything that can read data from the serial port can be then controlled with your Arduino and circuits as simple as this. I hope you enjoyed the tutorial. And remember, you have to build it, hack it, and share it because Arduino is you. Hi everybody, and welcome to another Arduino tutorial video supported by RS Components. Today we're going to look at the Arduino Wi-Fi Shield. It's a module that you can connect to your Arduino that allows the Arduino board to connect to a Wi-Fi network and then connect to the internet. And we can make all sorts of devices using this tool. Today, the example I'm going to show you, it's a simple lamp that changes color depending on messages that are posted on Twitter. So if somebody posts a Twitter message that begins with the hashtag Arduino RGB and then followed by a color represented as a 6-digit hexadecimal number. This is the way, for example, that colors are represented within HTML pages. The 6 digits represents the amount of red, green, and blue that goes into the color. The first 2 digits represent the amount of red, the second 2 green, and the last 2 blue. So what the Arduino is going to do is going to connect to Twitter, launch a search, and you will search for all the messages that contain this hashtag. And once it finds one, it will actually go search for the number, and then it will basically take every number, decode it, and turn it into an amount of color that will be represented on the RGB LED that you see here on the circuit. Let's have a look at the circuit. Here we have an Arduino Uno with a Wi-Fi module mounted on top of it. And then very simply we took a small RGB LED and we connected 3 resistors, and the 3 resistors go to pin 3, 5, and 6. There are PWM pins. So these pins are able to control the brightness of each individual channel in the RGB LED. So the module you see on the top here is the Arduino Wi-Fi Shield. The Arduino Wi-Fi Shield is actually a quite interesting device. It's made of this large chip in the middle. It's a 32-bit microcontroller that contains the whole software that's needed to process the Wi-Fi messages and connect to the internet and provide you with the whole networking stack. And it speaks to this little square module in the corner. That one, it's essentially the wireless part that communicates with the actual Wi-Fi network. So by using a powerful processor on board of the Shield, we can actually save code space, we can save memory on the main Arduino board. So let's have a look at the code. So in order to use the Arduino Wi-Fi Shield, we include the Wi-Fi library. And then we have, at the beginning, a couple of strings that represent the name of the wireless network we're connected to. So at this moment, we're connected to a network that doesn't require a password. So what it says, the next parameter contains just a word, a password that we're not going to use later. Then I have 3 pins, pin R, G, and B. These variables, they contain the number of the pins where the different LEDs are connected to. Then this constant max tweets indicates the amount of tweets returned by a search. I have to specify that most of the code that you see here actually comes from an example that was written by Limor Fried for the Adafruit Internet of Things printer. And I took this code and I removed the part that prints to the actual printer, and I replaced it with a simple piece of code that parses the information. There's another number of parameters that indicate how many times the frequency used by the Arduino to connect to Twitter. So in this case, for example, we're connecting every 10 seconds. And the timeout, so the maximum time we will retry to connect to the server before we stop connecting. And the timeout, so the maximum time to wait from data from the server. So there's a number of internal parameters that are maybe too long to explain right now. So we create a Wi-Fi client. We specify the server name. We specify the query string, in this case, Arduino RGB. Then I'm going to skip this rest of the code just to show you quickly how easy it is to connect to the Wi-Fi. So here we check if the Wi-Fi shield is actually mounted on the board. Then we check if we're connected. And then we just basically say Wi-Fi.begin SSID. If I need to specify a password, here after the comment, you see I can put comma pass, and that will specify SSID and password. And then we wait for 10 seconds. And that should be enough for a connection. And this is going to try and retry to connect to the Wi-Fi network until we're connected. Print Wi-Fi status will tell us, okay, you're connected, this is your IP number, this is the network you're connected to, and everything else. And then during the loop, what we're going to do, we're just going to create a connection to the server. We're going to send a request. This code I'm highlighting now is the one that sends the request to the server. Oops. And then later on, once the data is being received, it says here processing results. So we go to this function called JSON parse. JSON parse does quite a lot of work in processing the data that comes from the server, but what's interesting for us is here. Basically, I'm saying if the length of the message that we received is less than 20, it means that the message is short enough to be the hashtag plus the color. So I'm going to decode the color, print out the values I'm going to send to the LED, and I'm using analog write to set the color of each channel of the LED. And then we're just going to print some other debugging information if we want to know that everything worked out. And then we're going to reset the timestamp so that we can check in again 10 seconds. So here I'm going to bring in the debugging message. So if Davide, can you please send a tweet? So we're going to ask our friend Davide to send a tweet with a color, maybe send FF0000, so that represents the full red color. So now the tweet has been sent. It's going to take us a few seconds before Twitter stores the tweet and makes it available in the search. So at the moment you can see the log is just saying that it's waiting for results, there's no new result, pausing. At the moment, it's connecting every 10 seconds. So a message has been received, and you can see that there was a message, Arduino RGB FF0000, and our LED, it's now red. So based on this code, you can develop all sorts of other applications. So this could not be a lamp. This could be, for example, the watering your plants in the garden, or this could be the heating in your mountain home or something like that. So we could attach almost anything to this Arduino and make it Wi-Fi enabled. So thank you for joining us. I hope you enjoyed this project. And remember, build it, hack it, and share it, because Arduino is you.